And here I am with my last video of the evening that I should have recorded first. So 7C, the law of large numbers or the law of averages. Consider an event A with probability P of A in a single trial. The law of large numbers holds that for a large number of trials, the proportion in which event A occurs will be close to the probability P of A. Meaning if you do something enough times, like if you flip a coin enough times or roll a die enough times and count the empirical probability, it'll get close to the theoretical probability. The larger the number of trials, the closer the proportion should be. This law holds as long as each trial is independent of prior trials, so that an independent trial always has the same probability. All right. Now, it doesn't have to be the theoretical probability. If I flipped a weighted die or if I rolled a weighted die a whole bunch, I wouldn't get equal probabilities across the board, but whichever way it was weighted, I would consistently get that number more. So, a roulette wheel. This happens quite a bit, or, it's a big deal in Vegas. A roulette wheel has 30, and it should say 38 numbers, 18 black, 18 red, and 0 and 00 are green. So what is the probability of getting a red number on any spin? And if people spin the wheel 100,000 times, how many times should you expect or they expect a red number? So just on one spin, there's 38 numbers and 18 are red. So we can reduce that to 9 out of 19, which we can crunch as a number. So 0.4737. So 47% of the time, we should expect to get red. So if I spin the wheel 100,000 times, that's my theoretical probability. So 100,000 is a huge number. So I should get 9/19, really close to that of 100,000. So to crunch that, we literally 100,000 times 9 over 19. And we get 47,368.4. So a little over 47,000 reds. Now we may not get exactly that, but it will be closer to that. Now another thing we have is expected value. So we have two events, each with their own value and probability. Expected value is based on these two events. So it's the value of an event times the probability of an event. And then you add the value of another event times the probability of that event. And you can keep doing that for however many events are going to occur, or the value of different possibilities of the same event. So this often comes up like this, lottery tickets. So $1 lottery tickets, we're just going to suppose have these nice properties. 1 in 5 to win a free ticket, 1 in 100 to win $5, 1 in 100,000 to win $1,000, and 1 in 10 million to win 1 million. So what's the expected value of a lottery ticket? All right, so we're going to crunch the numbers. So here, this first one, I bought a ticket. That means I spent $1. And the probability is 1. I have to do that in order to play the game. This is a common thing people will forget, is the cost of the game. So this is -1 times equals -1. Now we are going to have a gain of $1, but that only happens 1/5 of the time. Then we have a gain of $5. The cats are being crazy. That happens 1/100th of the time. So 0.05. And then 1,000 times 1/100,000, 0.01. And then 1 million over 10 million will be 1/10. So I'm going to write it this way. All right. So now we add all of those and see what the total is. So this is -1 plus 0.2 plus 0.05 plus 0.01 plus 0.10, -0.64. So what this means is if I bought a whole bunch of lottery tickets, I would expect to lose money. So for every dollar I spent, I would expect my winnings to only recoup 36 cents, leaving me 64 cents in the hole if we did it a whole bunch. So you can still win with one ticket, but on the whole, it's going to be a losing prospect with your partial amounts you can win in there. And working this kind of formula on the lottery, the real lottery, can be kind of eye-opening. Although crunching it for all the in-betweens can be a little crazy. Now we have an art auction. The cost of the painting is $50,000. You believe that you have a 1 out of 2 probability of reselling the painting to a client in New York for $70,000 and a 1/4 probability of reselling the painting to a client in San Francisco for $80,000. Otherwise, you will have to keep the painting, resulting in a loss of $50,000. So what's the expected value of this bid? So in order to calculate this, the first event that must happen to even consider this is that you spend the $50,000. And so our probability here would be 1. So the expected value is -50,000. Now, half of the time, I'm expecting a gain of 70,000. So that results in a positive 35,000. And then I'm expecting 80,000 1/4 of the time. So that gives me 20,000. So when I add those three up, we actually do come out with a positive number. So it's up 5,000. Now, this doesn't mean I buy the painting and then suddenly I have 5,000. It means if I bought a whole bunch of paintings with these probabilities, on average for each painting, I'd expect to gain about 5,000. meaning I'd keep a couple of them, but I'd sell some others for a profit. And so it would average out to $5,000 per painting. But the reality is we do not have $50,000 to buy the painting. That's why this is a ridiculous problem. The gambler's fallacy, the mistaken belief that a streak of bad luck makes a person due for good luck, also called the gambler's ruin. So we're going to play around with this concept a little. So pretend you're playing a very silly coin toss game where you win $1 for heads and you lose $1 for tails. After 100 tosses, you have lost $10 because there were 45 heads and 55 tails. So you decide to keep playing because your luck is bound to turn around. After 1,000 coin tosses, there are 480 heads and 520 tails, so you got more heads. Does this agree with what we expect from the law of large numbers, and have you won any money? So after 100 tosses, you got 45 heads. So that is 45 out of 100, which equals 0.45, which equals 45% for heads. After the 1,000 tosses, we have 480 out of 1,000, which gives us 0.48 or 48%. So the law of large numbers says the more trials, the more times you do the thing, the closer what occurs should get towards the theoretical. So the theoretical with a coin is 50-50. So after 100 tosses, I was at 45%. After 1,000, I'm at 48%. So I am getting closer to the half. And this is like just counting it up at the end. So it's not like he got 480 heads and then 520 tails. You know, some crazy mix. So it's getting closer to 50-50. So that is definitely agreeing with the law of large numbers. Now, have you won any money? So 480 heads, I gained $480. And then 520 tails, I had to pay out 520. So I'm actually in the whole $40 now. So still haven't won any money. It's not a good game. Eventually it would average out, but eventually can take a very long time. Alrighty, that's it for C.